Let's talk about halogenated benzenes. So we've looked at halogenated benzenes before when we were discussing reaction rate. And what we learned is that halogenated benzenes undergo electrophilic aromatic substitution at a rate that's slower than just regular benzene, right? And so what we spelled out, we looked at the relative rates. And so if we make the relative rate of benzene at 1.0, right? So we're just looking at how these relate to benzene, right? We learned that the reaction rates are slower, and it's not in a trend that you would expect. And so the relative reaction rate of organofluorides is going to be 0.15. The relative reaction rate of organochlorides, 0.033. Organic bromides, arylbromides, 0.030. and aryl iodides 0.18, right? So you can see it actually adopts this kind of U-shaped rate trend where the fluorides and the iodides are going to be the fastest or undergo substitution the fastest, and the chlorides and the bromides will undergo substitution the slowest. There's a reason for that, and in this video I hope you'll be able to predict that. We are going to take a look at that reason. Right. First of all, we need to lay out, right, looking at this rate data, we can say that halogen atoms are deactivating groups. All right, so that means that reactions will be slower relative to benzene. All right, and we can pretty easily understand why that is. If you take a look at an electronegativity table, right, you'll see that each of these halogen atoms is actually more electronegative than the carbon that it's attached to, right? So carbon has an electronegativity of 2.55, all right? And fluorine has an electronegativity of 3.98, right? So obviously that's going to be a highly polarized bond. And so fluorine is going to be pulling electron density pretty strongly out of that ring, or at least away from this carbon. All right, chlorine has an electronegativity of 3.16, right? So not quite as electronegative as fluorine. Nonetheless, it still is going to polarize that bond significantly towards chlorine, right? As we get up to the bigger bromine atom, now we're dropping down into the twos. Bromine has an electronegativity of 2.96. Right, so still more electronegative than carbon, right? But you can see that we're losing that pull on those carbon electrons, right? And finally, iodine has an electronegativity of 2.66. So not much of a difference between carbon and iodine, but still enough to deactivate that ring a little bit, right? So you can see that each of these is pulling a little bit, at least a little bit, of electron density out of the ring. It's going to make that benzene less reactive and therefore decrease the rate of electrophilic aromatic substitution. Right? The other thing that we have to write down for electrophilic aromatic substitution on halo-benzenes is that halogens are ortho-para-directing. Right? And this is probably a little bit unexpected, right? So we've learned so far that electron withdrawing groups will deactivate a ring and will direct substitution to the ortho-para position, or sorry, to the meta position. Right? This is a case where we have an electron withdrawing group that deactivates the ring, right, but directs in the ortho-para position. The reason why this is because each of those halogen atoms have 3 non-bonding pairs of electrons. And therefore, they can each stabilize the ortho-para-arenium ions. All right, so let's take a look at that trend. All right, so we're going to just look at how that can happen. We're going to look at the carbon of the benzene ring, right? And then we're going to take a look at the halogen that that carbon is attached to, right? So in this case, this is fluorine. Okay, and so when we think about those 3 lone pairs of electrons on fluorine, in order for them, at least one of them, to interact with the ring, they have to be elevated to a p orbital. So here's the p orbital on fluorine, right? And we know that this is a 2p orbital. And here's the p orbital on carbon, right? And we also know that that's a 2p orbital. Okay? If we look at carbon and chlorine, right? Here's the 2p orbital on carbon. Right? But now chlorine is using the 3p orbital. So compared to the 2p orbital, the 3p orbital is going to be a little bigger. You would imagine if the 3p orbital is a little bigger, it might not be able to overlap as well with carbon. Okay, if we move on to our carbon-bromine bond, put a positive charge in these. All right, and draw our 2p orbital for our carbon atom. Right, now for the bromine atom, we're using the 4p orbital. Right, and so now that's going to get really big. And so you can imagine the overlap with between the 4p and 2p orbitals is going to be relatively poor. Right? It's like Andre the Giant shaking a baby's hand. Okay? And then finally, if we look at iodine, right, iodine is going to use the 5p orbital, which compared to a 2p orbital is tremendously large. Much farther away from, those electron densities much farther away from the nucleus on average. Right? So in this case, there really is not going to be much overlap between iodine lone pairs and carbon. Right? And so this might help explain the trend that we're seeing above. Right? So fluorine is the strongest electron withdrawing group. Okay? But it's also the most able to donate an electron pair into the ring. Right? Iodine is the weakest electron withdrawing group. Right? So it's not removing much electron density from the ring, but its ability to donate into the ring is pretty small. Right? Chlorine and bromine are in the middle. And so that's why we see this U-shaped curve, right? Here, fluorine has the best ability to donate electrons, right? Over here, iodine is the least electronegative, okay? And so it's not deactivating the ring quite as much. And that's why we see that trend in the rate. All right, so again, it should be noted that whenever we have a halogen, we would expect to see ortho-para substitution, even though that reaction might be slow. All right, so if we take an organochloride, an aryl chloride, and do a nitration, what we expect to see is that our major products are going to be the ortho-nitrophenylchloride and then the para-nitrochlorobenzene. All right. Again, the exact distribution of these two is going to depend upon the conditions of the reactions, but we can, we can expect somewhere in between I would say a 1-to-3 ratio and a 1-to-1 ratio, right? And so we can adjust those conditions to maybe favor one over the other, but know that the major products in this reaction are going to be the ortho-substitution product and the para-substitution product. All right, so now we've had a look at a lot of different substituents and seen how those substituents affect the rate of the reaction and also the regioselectivity of the reaction. In the next series of videos, we're going to look at some of the practical applications of electrophilic aromatic substitution, apply this family of reactions to this synthesis, and maybe look at some of the finer details of the reaction as well.